Hello everyone, this is lecture 11. Today we're going to talk about transient flow in a confined aquifer. So the learning objectives of this lecture 11 is to describe the TS equation that models the transient drawdown with the time in confined aquifer. So far we've set the condition as a steady state so that the drawdown curve or water table didn't move. But here we're going to talk about how this water table will change. The location of the water table changes with time, and that requires the analysis of the transient flow. And the second is to derive the Jacob approximation and in what condition we can use this Jacob approximation. And then lastly we'll talk about the radius of influence using this Jacob equation and understand the parameters affecting the L, this radius of influence. Right? So the first, development or drawdown with time. So when the time is limited, and relatively the drainage is very slow, then it becomes the transient flow. So for example, like 1 year later, where the water table will be located. And to analyze and to predict this water table location or drawdown curve, we used this equation, which is developed in the 1935. And here, we're going to talk about the confined aquifer, because the confined aquifer is simple and it's very robust equation. So let's say that we have a confined aquifer with the thickness of B, and there's a well is fully penetrating, and so the location, the original water table location is here, and as you pump out, you have the water table lowered like this, and we want to know that what's the location of water table or the drawdown with respect to the distance from the well R and with time T. And here the UR is the flow rate into the well. Here the assumptions for this equation is the aquifer is homogeneous and isotropic and large. And the second is that the original piezometric surface is horizontal. So here the water table is originally horizontal, and the well is pumped at a constant rate, Q, and the well is fully penetrating and the flow rate is horizontal. So here the well is up to the bottom of the aquifer, and also the water is flowing horizontally into the well. The well diameter is negligible so that the storage within the well can be neglected. So here we're gonna introduce some parameter that we learned in the previous class, which is the storage coefficient S. And here, because the volume of the well is very small comparing to the this aquifer, because aquifer is very large, so that we can neglect and we can ignore the well volume. And there's no recharge in the time of pumping. So during the pumping, there's no recharge. And Dupit theme approximation is valid. So let's derive the one-dimensional continuity equation. And this equation is S over T, round H, round T, plus 1 over R, round H, round R. So the reason that we have one more term here is that because it's axis symmetry condition. So we have a radial distance R, and we have a radial coordinate here. And here the S is storativity or coefficient of storage, and the T is transmittivity. I think we've talked about transmittivity in the previous lectures, which is T and this T can be calculated by multiplying the hydraulic conductivity times the B, the thickness of the aquifer. And there are some boundary conditions that we can get. The initial condition, the head is constant everywhere. So H, R, 0, at the time of 0, the H naught. So in everywhere, so you have a flat piezometric surface. Right? So this is the H naught. And when the R is sufficiently far from the well, so that the R is somewhere here, right? Further than the influence range, then the piezometric surface is H naught, regardless of time. And continuity, the second boundary condition is continuity at the well, so in terms of the flow rate. So the flow rate Q is 2 pi R times minus UR, because the water is coming in. And here the UR is the flow rate into the well for the thickness of the well. And so that this UR can be expressed with the this transmissivity times round H over round R. This is the hydraulic gradient. Then using these two boundary conditions, we can solve this partial differential equation. Then you get this solution. So H naught minus H R comma T, or H naught minus H, is Q over 4 pi T times the integration of this function. And here the W is a dummy variable for the integration. So it's an arbitrary variable of integration. And so you have a U as a parameter in this integration. So this integration is function of U. And here the U is defined by this equation, R squared times S over 4 times T times small t, so which is time. And this integration part is called this well function, and this well function can be symbolized with capital W, which is function of U, and you can solve this function using calculator, or in the handout. I'm gonna distribute this handout in the class during the class, and you can find the W using this U. So if you know the U, then you can find any W using in this table. We're gonna talk about that. We're gonna see how we can calculate the W in the class using some example. So H naught minus H is the drawdown. Right? So here H naught is the original piezometric surface, and H is the current piezometric surface at the distance of R. So then H naught minus H will give you the drawdown at that location and at the time of T. So S R comma T is Q over 4 pi T times W U, which is this well function. So in the class, we're gonna have some example to use this equation to get the drawdown around the wellbore in the confined aquifer. And Jacob's approximation. So this well function can be also expressed in terms of the infinite series. So then WU is minus gamma minus ln U plus U minus U square of over 2 times the factorial of 2 plus U to the 3 over 3 times the factorial of 3, right? then etc. etc. You can go over and over. And then here the u is also defined as the r squared times s over 4t and small t. And here gamma is the Euler constant, so 0.5772 is typically used. So if the pumping rate is pumping time is large, so the t here is large, and if the r is small, then the u becomes small, right? So when the when u, let's say that u is 0.01, then the w, this wave function, you can also calculate using this infinite series. Then it becomes 4.03. And also in the table, 0.01, so that's 10 to the negative 4, so that's negative 2, so that's this number, right? 4.04, right? 4.038 or 4.04. So then this w from the infinite series and the w from the table is pretty much close, very close to each other, so it's acceptably equal. So then, which means that when u is less than 0.01, then this approximation can be used. And for the second term here, so because the u is less than 1, then as this power increases, that value will decrease, right? It's going to be very small. So then, and here the gamma is 0.5 or 0.6, so then the u, if the u is 0.01 and gamma is 0.57 something and something, then you can see that the difference is very big. So you can just take these two terms, the first and second term, to calculate this wave function. So according to the Cooper and Jacob, they suggested that we can just use the gamma, the first term and the second term, as an approximation, so that the w is minus gamma minus ln u, and then this can be included in the logarithmic function e to the negative gamma over u, and here the gamma, we know the gamma, right? So then we can calculate this part, which is 0.561 over u, and u is here. So then we can just plug the u to this equation, then you get this final. So then the previous equation here, the Jordan equation, can be simplified using this Jacob approximation further. So the final equation becomes S r comma t q pi t ln 2.25 t small t r square s. And one more thing is that here in the function of natural log, the t is transmittivity. So transmittivity has the length over time, the dimension of length over time, and here the time, so it can cancel out. So you have a length square in the upper part, and then you have a r square, it is length square, and the storage coefficient has no dimension, so it's a dimensionless parameter. So you can see that if inside this parenthesis, you will just all cancel out, so that you have a dimensionless parameters to calculate the logarithmic value. Then next up is, so using this Jacob approximation, we can also calculate the radius of influence. So if you look at this equation, the S is function of Q and the T and the R and the S. So here it can be used to estimate the strativity, or storage coefficient, and transmissivity, the large T, and the radius of influence L. So let's derive the equation for the radius of influence L. So then the distance, so this radius of influence is defined as the distance from the well to where the drawdown is negligible. Basically, the S should be 0. So that S is 0, where the Q 4 pi T ln 2.25 pi T over L square S. And because the Q is some value, has some value, it's not 0, and T also is not 0, so that this should be same with the 1, right? Should be identical. So 2.25 T times small t L square S becomes 1. So then if you solve it for L, then L is 1.5 square root of T times small t and S, large S. So this is the final equation to get the influence radius. And this influence radius is, you can see that it's a function of transmissivity and the time and the storage coefficient. So as time increases, so as you pump in more, then the radius of influence will increase more, right? So it's going to increase more from here, it's going to increase more. And as the storage coefficient is small, then you have the larger L. And as the transmissivity increases, also you have a larger L. So let's think about the some aquifer, confined aquifer with the thickness of B. Then T transmissivity is K times B. Right? S is alpha plus beta times N. So then means that so to have a large L, the beta should be small, right? So beta should be small, and S is small, so then L will increase. So that means that what? This is the compressibility of the water, or let's say the alpha. Alpha is compressibility of the soil, right? So then, so the soil matrix should be stiffer. So as the stiffness of the soil increases, then alpha decreases, so that you have a larger L. So more stiff soil will have a larger L. And what about the K here? As the K increases, T increases, so that the L also increases. So high permeability soil, like sandy soil, will have the large L. And however, you can see that from this equation, it doesn't have Q. So L is independent of the discharge rate, Q. So Q only affects the drawdown S within the L. So from here, from this equation, Q affects the S. Right? So as the Q increases, the drawdown will increases. There's a linear relationship between that. So the influence L will be fixed. It's not affected by the Q, but as Q increases, it's gonna be draw down more. Right? So this drawdown will decrease further below as the Q increases. Okay, so today, let's wrap up. We have looked at the TS equation that can model the transient drawdown with time in a confined aquifer. And we also looked at the Jacob's approximation as a function of U. And the Jacob's approximation is only valid when the U is less than 0.01 or something. And also we calculated the radius of influence. We derived the equation to calculate this radius of influence using this Jacob equation. And the radius of influence, L, is affected by time and transmissivity and the storage coefficient, but not by Q.